All right, we're live back again for CNBT 1311. We're still in Chapter 3. This starts foundation walls. Now, we have discussed foundation walls previously we're going in the wrong direction. Let's get the full picture here. There we go. We've discussed foundation walls in previous videos dealing with retaining walls and such as that. Now, based upon our current definition, this is the foundation down here. This would be the superstructure, and this would be starting this is a substructure, I'm sorry. And this is the superstructure up here. Whether it's a high-rise building, whether it's low-rise, mid-rise, or a residential section. It's residential, this would be a basement. So let's see what we have here. All right, let's enlarge this just a tad. All right, let's start at the bottom and work our way up. Okay, the size of footing is based on the foundation wall load, and it's based on the allowable bearing capacity of the underlying soil. And we've talked about that through soil mechanics. And it also has to take care of all the loads of the building, yes? The foundation system must transfer all the lateral loads on the substructure to the ground. It must take care, now again, I expect y'all to read all of this. This obviously has some groundwater issues, or there wouldn't be a subsoil drainage system with granular material. If you're going to do a French drain like this, you're going to need some kind of textile fabric, and there needs to be some waterproofing along this wall all the way up. Damp proofing, you use waterproofing. Not damp proofing. And again, this is a diagram of the active soil pressure. And if the water table rises, you've got more than just the soil. You've got water also pushing against the wall. Now, depending on how deep this wall is, where do you think this drain has to go? I mean, water doesn't flow uphill, so it's got to go somewhere. All right? Does it go to a sump and then has to be pumped out? These things have to be accounted for. You just can't just stick a wall in and be done with it. I guess if you're out in the desert, you could. They don't get much rain out there. So let's look at the rest of this detail. All right. This is a concrete ground slab. It's a slab on grade. If this really was a basement or a sub level, which it obviously is, because here's the top of the soil, and this is underground, then what's going to happen? You got the propensity for water, since you got a drain here, water to mitigate up through this slab and leak inside your basement or substructure area, and that's bad. I would not recommend to my architect to design it like this. This would be a monolithic slab. If we needed big spread footings down here, that'd be one thing, but then I'd have a construction joint in this wall with a water stop, be it an elastomeric water stop or whatever, and then I'd have a cast in place slab. Now, depending on how big this is, now this shows a pre-molded filler or sealant at the expansion joint, so they're looking for to control some expansion in this slab. So we don't know how big this is. We don't know how far this span is. There are other ways to handle this than just a sealant. Okay, you could use a PVC water stop, which is flexible. We use this in wastewater treatment plants a lot. So if this needed to be an expansion joint, If that needed to be an expansion joint that was cast again, then this would be the wall, the concrete wall, and this would be the slab. Um, these joints are very problematic, so they have to. This detail can cause you a great deal of grief if you're not careful how to handle it. I'm not saying this is a bad detail. I'm just saying that this is a potential for water mitigation. Just because you put some sealant in that joint doesn't mean that it's going to seal. Water is really a nasty devil. Okay? Now this detail does show a keyway right there for the wall. There are the steel reinforcing coming up. For thermal insulation options, you see Chapter 7, cast in place concrete. If you built one of these out of masonry, I'm going to fire you. If you build one of these out of wood, I'm going to commit you. These things need to be out of reinforced concrete, in my opinion. All right. If you work for me and you come in here with a wood foundation wall, I'm going to fire you in a heartbeat and see if I can get you committed. Masonry is another bad choice. Reinforced concrete is a lot denser than CMUs, and water mitigates really bad through those things. Moisture vapor. It's not just the liquid water, but it's also the vapor. It's the dampness. Okay. He makes a good note here. When enclosing a habitable space, a foundation wall system must be constructed to resist the penetration of water and soil gases such as radon. Oh no! Control heat flow, accept a range of suitable finishes, and accommodate windows and doors and other openings. You're going to put a window and door down here underground? No. Okay. The bottom line is the perfect wall is what? Again, the perfect wall is moisture resistant, vapor resistant, air resistant, and thermal bypass resistant. So these walls are no different than a wall up here. All right. Except these have a constant nastiness to them. All right. This represents the gravity load down the wall. This represents any lateral load resistance from wind or shaking or whatever. Here's your floor system, and then here's your wall system up here. And these things need to be pinned. They got to be pinned somehow. Depending on what your floor joists are, they've got to be pinned. All this has to be tied together somehow, some way. And that's where your structural engineer and your detailing come into play. All right, crawl spaces. This is a small area underneath your spread footings or your piers or whatever you want to call them. Crawl spaces are not that popular down in this area anymore. Older houses out in the country have crawl spaces underneath them. Crawl spaces can be a blessing and they can be a curse. There's an architect in Austin that uses crawl spaces, and he actually puts some form of air conditioning and heating in these crawl spaces to balance out the temperature differential in the floor systems. Okay. But again, that can be a blessing or a curse. The benefit of the crawl spaces is all your plumbing and everything can be underneath here. So you don't have to worry about 30 years from the house being built having to reroute the plumbing outside because the slab is settled a little bit and you got a belly in the pipe. You can come in here and repair the piping or whatever. And you can also adjust the level of your house under the crawl spaces. So again, that's a blessing and a curse. All right, foundation walls. Okay, more foundation walls. You design me a wall like this. This is fine. This is reinforced concrete. I have no problem with this. This starts to become a problem. The CMUs are not dense. They're not near as dense as reinforced concrete. and they will pass water vapor and water through this wall much quicker, much easier than this, and you'll end up with a lot of latents and dampness and mold in your substructure area, your basement or whatever. All right. Plus, these things have to be constructed properly. You've got to watch the mortar. These things have to be reinforced, and the cells have to be filled with concrete. Okay. I'm not a big fan of these. These, yes. Yes, this costs more money. Yes, this costs more money, but it's more permanent. And if done properly, it will outlast these. Now, connecting your subfloor to your foundation walls. Where's that other nasty detail? Somebody had another nasty detail in here. Okay, all right. And there's several ways to do this. You can put a crib beam, a ledge on the foundation wall. You can put pockets in the wall. You can put a plate on top of the wall and use anchor bolts in there, and then you'll use steel plate anchors or hold downs on your fascia board that comes in on your joist. Okay, here's a side detail. It's a typical stud wall framing. There's your anchor bolts that are set in place when they cast the wall. And there is your seal plate. And yes, it better be pressure treated. And then there's your header or rim joist. And there's your floor joist. And then there's your substructure framing, whether it's wood or steel. If you're using bar joist, which are trusses, then you can embed steel base plates anchored to the concrete foundation or wall and set the bar joist on them. I would embed steel plates, and then the upper flange of the bar joist, the upper chord of the joist, then you can come in and weld them. Okay. Let's see, what are they doing? They're pocketing out masonry on top of the that's not a good detail. That's not a good detail at all. If you're gonna do a masonry superstructure, you need to come up here and do pockets. Just cast pockets in with this wall, and that's a part of that. And then the masonry can set on pockets. That's expensive. That's an expensive detail. Or what you can do is you can put a ledger beam across here, like a lintel, and fill that gap in. Okay. There are more foundation wall details. This is a double wythe construction. A wythe is a roll of masonry, a wall of masonry. Here's two wythes, exterior and interior. You have this air gap in here. Again, what's the perfect wall system? Vapor. What is it? It's vapor, moisture, air, and thermal bypass, right? So you'll need some kind of flashing in here. Here's some damp proofing. I wouldn't stay away from damp proofing and go to waterproofing. He defines damp proofing may consist of a bituminous or acrylic modified cement coating. I would be very suspect about coatings. Everybody sells something that's supposed to be the greatest thing since sliced bread. Waterproofing membrane over something like a bitumastic coating, like coal tar epoxy or something like that. it's probably better. Um, uh, Waterproofing opens up a whole area of expertise. So what are you trying to waterproof? How much hydraulic head? How much water pressure? Okay. Um, some people, he talks about gravel backfill. That may or may not work for you. The problem with gravel with certain soils is eventually the granular material mixes with the soil and you lose your French drain. If you're going to do a French drain, you need to have a geofabric around the whole French drain so the soil doesn't contaminate the granular drainage of your French drain. Okay, and he gives you some rules of thumb down here. Again, you want to get back with your soils engineer for that. Oh, here it is. Where are we at? Come on. Oh, we're at 16 minutes. Has it really been only 16 minutes? Wow. Okay. Treated wood foundation systems. If you do a subterranean treated wood foundation system for me, I will fire you in a heartbeat and try to get you committed. This is a haven for everything from termites to rot. And there's all kinds of different rot. There's direct water rot, there's dry rot, which is wet and dry cycling. This is just a bad, 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 did I say bad? Design. Don't do it. Don't do it. Now, if you're on a desert island and this is the only thing you've got, well, you're on a desert island. I don't know why you'd be digging a pit anyway, but nonetheless, don't do this. This is a bad idea. I don't care what anybody says. Okay? The American Plywood Association back in the 70s had a whole manual on this, okay? And their treated plywood was supposed to be absolutely impervious and blah, 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 blah. Don't do it. Do not do it. If you're going to have a subterranean wall, make it out of reinforced concrete, something that works. You bury wood, it's going to rot eventually. I don't care what you do to it. Enough said on that. I'm done. We're moving on. Column footings. Sounds like we've been here before, doesn't it? Okay. Column footings. All right. Here's a typical footing. You go back to the minimum temperature steel. That may or may not be. You may have another row up here, depending on how loaded these footings are, depending on how much moment's coming down these columns. All right. Depending on how big that footing is. All right. And then you'll have your dowels coming up, your rebar dowels out of the footing. They didn't do the keyway in here. All right. Then you'll form your column up, whether it's a square or round column. He likes square columns. All right. They may just drop a sonotube in here, which is a round column form. Your vertical reinforcement, and then this is your lateral reinforcement, are your ties. If you cut a section through this, if we cut a section through this, it's going to look like this. This is the section. Okay, this is well, that's a nasty A. All right, that's section A. Just pretend that's an A. All right, so it's going to look like this if we cut a section through there. There's your reinforcement steel. You may get by with just 4. You may have a lot more depending on how loaded the column is and what the American Concrete Institute code says after you do your calculations. Again, this is not a structural engineering course. And then these are ties that hold the column still together. All right. The area is the contact area. So P is the column load in pounds, R kips. And A, the area, is P over S. You know, S is your soil bearing capacity. All right. So, okay. And I don't know why he's using kilopascals, but I guess it's a European thing. It's a metric thing. But nonetheless, okay. So you divide the area of your footing by the load and over the soil bearing capacity, and that's how big you know to make your footing. Plus, the footing has to be what? It has to be big enough to take care of the shear force from the column, right? Which comes down at about a 45-degree angle. So the footing may actually have to be bigger than what the load bearing capacity of the soil says to take care of the shear force from the column. Because this downward force coming down from up here, it's going to spread out. And if it spreads out over here, then the footing needs to be bigger, irrespective of what this says. Okay. There's another way of handling wood columns, like on a portico or patio cover. You've got concrete footing, and then these are cast in the concrete footing, and there is airspace under here. There's a variety of proprietary. That just means that somebody manufactures them for bases. Strong Tie makes tons of these. A word of warning on something like this. This wood post comes down like this. Well, it's supposed to come down vertical. And then we have this right here. And we have this right here. All right, coming down into the concrete footing. My goodness. Man, you would think I had like Parkinson's disease or something. And here's your footing. You are going to want a space underneath that wood column and the surface of that concrete so that when it rains, that water doesn't stand up underneath there and rot the bottom of that wood column out. And that column is only supported by those bolts in shear. So it's not going to carry a whole lot of load. Now, if you want that wood column to carry a lot of load, then you're going to need to try to get some expansive non-shrink structural grout, which is different than cement, and force that underneath there. And force that underneath there. If not, you're going to have a rot problem. It will rot out. Now here is a steel column, steel base plate, to distribute the column load over an area wide enough that the allowable stresses in the concrete are not exceeded. That goes back to that shear stress, shear strength diagram at 45-degree angle. And then you'll notice that these base plates are grouted. And they're not grouted with cement. They're grouted with a non-shrink structural grout, which is a whole lot different than regular cement. It's not grout that you'd use for tile. It's a non-shrink, non-shrink, expansive structural grout. All right. Foundations on sloping ground. This shows a 45-degree angle of repose. This shows a 45-degree angle of repose. You want to set the face of your structure away from the toe of a rising slope to provide protection from the site drain. Remember we told about the rain coming off and washing down around here? You don't want it undermining your foundation. Set your face of your footing back from a descending slope, a distance sufficient to provide vertical and lateral support for the footing to prevent settlement. What about erosion over the years, over the life cycle of this structure? You think that's going to stay there forever? Not if it's got an angle of repose, and not if you don't have some sort of erosion control on this. All right. He gives you a rule of thumb for this. Um, um, I would go back to your soils analysis and your soils engineer, okay? Um, and you may actually need to invest in some erosion control to maintain this, okay? Um, or if this is your property line here, you might just need to bite the bullet and put in a retaining wall, and then supply the drainage through weep holes in the retaining wall. But then again, that depends on who owns this property over here, and your site constraints, and your zoning ordinances, and everything else. All right. Closely spaced footings or adjacent footings located at different levels can cause overlapping soil stresses. If this is a shallower footing, this footing is going to stress down through here, and it could impact the load capacity of this footing. Again, this goes back to your soils engineer and your structural engineer. And he gives you some rule of thumb: 60 degrees for rock, 30 degrees for soil. Somewhere in between there is the magic 45 degrees. Again, this 2 times the footing with the minimum. These are all rules of thumb. They're not to be, I wouldn't be betting my life savings on this. Use your soils engineer and your structural engineer to guide you in this. Ground surface should not encroach on the bearing prism of soil or rock. Well, that's true. All right. Stepped footings change levels in stages to accommodate a sloping grade and maintain the required depth at all points around a building. Okay. In other words, here's the grade, here's your retaining wall, or your structural wall, all right, and your grade is sloping down the wall. Okay, and then what are we going to have here? What is this? The length of your step. And what is that for? It's for erosion control, is it not? All right. Again, your structural engineer and you and your architect should, or your soils mechanic, your soils engineer, should be able to guide you on this. So what this means is this footing is stepping up. Okay. So this footing does not go all the way back, super deep back in here where you have to do a deep excavation. You're basically benching or stair-stepping that footing. Those are a real pain. Tightly spaced houses in areas that have sloping topography often have to do this. And generally the road is out here someplace, and then the high point of the hill in the back of the house. So part of the house is underground, as we've seen before in some other details. All right, concrete slabs on grade. We've talked about concrete slabs on grade. They can be placed on at grade level or below grade level. The support of a level, stable, and uniformly dense or properly compacted soil. We've already discussed that. He gives some details here which generally don't happen around this area. You have your typical small residential house, 4-inch slab, and I'll fire the builder if he uses welded wire fabric in my house. I want reinforcing steel, not welded wire fabric. There's a vapor barrier that keeps your concrete slab from sweating. And this is 2 inches of sand compacted, and then some kind of granular material. Now, we don't use a lot of granular material down here. We use a lot of sand if they've got it. My 50-year-old house, they did not do this when they poured the slab. I've jackhammered through the slab, remodeling the bathroom, and the people that built my 50-year-old house were Well, let's just move on. And then this is supposed to be stable, uniformly dense soil. Okay? And what we mean by uniformly dense is it's compacted to at least 98% compaction based on the soils analysis. All right? And he gives you some rule of thumb here: maximum slab dimensions, wire spacing, and wire size. Okay? Again, do not rely on this chart. It could get you in trouble. It might work for you. It may not. Anyway, use your structural engineer. Concrete slabs on grade. Again, 3 types of joints may be created for construction in order to accommodate movement. Now, this is important. You have isolation joints. We spend a lot of time on other stuff that you may think is not important. These are important, these definitions on 319. Isolation joint, construction joint, and control joints. Whether it's a road or whether it's a driveway or whether it's a slab on grade, you need to understand the difference between isolation joints, construction joints, and control joints. Isolation joints, often called expansion joints, allow movement to occur between a concrete slab and adjoining columns and walls of a building. Okay. Construction joints provide a space for construction to stop and then continue at a later time. These joints also serve as isolation or control joints. They can be keyed or doweled to prevent vertical differential movement, but allowing slab sections to move apart. You'll see a lot of construction joints like this in roadways, with the exception that there'll be a key on one side that'll hold this rod. The rods will be greased, and there'll be a can over here, and it allows the pavement to expand and contract. And then there'll be a compression board. He calls it a prevent bond in that joint. That's okay for a roadway, but for a slab, then you really would like it keyed so it can move this way, and it helps with mitigation. Control joints create lines of weakness so that the cracking that may result from tensile stresses or shrinkage when the concrete's curing will have a place to crack, and it won't be unsightly. You can saw them. You can come in after the slab's poured while it hasn't reached its full strength and saw cut these on a pattern, or you can pre-mold these things. You just put in a pre-mold, set them in a metal strip inserted when the concrete's placed. Or sometimes they'll come in with a rake. There's a special tool. It's got a long pole on it. And while the concrete's wet, they'll, well, that's a bent pole. And they'll run that across the slab for a control joint, okay, in some cases. I've seen them do it a lot. Key joint, this prevents a bond by using a preformed metal or plastic joint material by applying a curing compound to one side before the other space. And all a curing compound is, it's really to keep that concrete from bonding, and it works as a control joint too. And as you can see, the key keeps the thing from lifting up or moving around, up and down. Here's more details of slabs on grade. This is a masonry wall. Again, I'm not a fond of substructure masonry walls, but some people use them. Actually, this is a cast wall, and you're putting the masonry up here. I think that's what he's trying to tell you. Whether it's a single wide or it's a concrete block masonry wall. And Some people will float their slabs, their slab on grade. There's nothing wrong with this. Again, if you can tie that slab in with the wall, and you can take care of any moisture mitigation at the edges, at these edges with an isolation joint. Okay? Nothing wrong with that. This would be an example of an interior where you have either a load-bearing wall or a footing. Well, you got a footing, but this could either be a masonry load-bearing wall, or it could be a footing coming up, and then you have an interior wall, whether it's wood, steel, or masonry up from there. I would not extend my wall below this line. If you're going to do this, it needs to be in there, and that way your wall material is not below the grade for termites and stuff like that to wick up into your house or your structure. Here's another detail of a stud wall. This is a typical wood stud or metal stud wall. This is extruded polystyrene foam insulation, maybe placed underneath here. Cast in place concrete or concrete masonry foundation wall. Hopefully it's cast in place concrete. Here's a grade beam in a slab on grade with a wall on the grade beam to carry the load of the structure. You may need to thicken that slab. Again, your structural engineer will be able to help you. And this is a exterior grade beam. He calls it a thickened edge slab, but it is a grade beam because it is a beam under the grade. And here we have a monolithic slab pour with the grade beam. This slab would then maybe extend up to here, and this would be in the center of the house or the structure for a load. Your mileage is going to vary. Trust me, it will vary. Okay. Concrete slabs on grade steel. I told you about heated ducts in slabs where they run hot water piping in the concrete slab to heat the slab in super cold areas like up in Colorado and such. You're going to want insulation on the outside, and it's just a whole heating grid that's in the slab, and keeps the house at a constant, the slab at a constant temperature, because the heat rises into the house. Let's see, embedded heating pipes. No, here's the embedded heating pipes. Well, they'll pour a cover slab over the pipe grid. A lot of them in Colorado are just, they're in the grids in the cast in place concrete up in here. There are several ways of doing this. Pipe penetrations through a slab are a problem, especially down here where we have a lot of termite problems. Those things need to be sealed, and they need to have a way of getting in and inspecting them to see if termites are damming up into your structure. Even if you put foam plastic insulation and seal all this stuff. All right. Slab steps and slabs. We'll talk about stairs and steps later, but these things will get you sued if they're not designed properly. Tripping hazards and such as that. We have a whole section on stairs later. Slab openings larger than 12 inches, extend a second layer of wire mesh reinforcement on all sides. Generally what we used to do is we would put extra rebar in around these large openings. Extra rebar. And why is that? because of that diagonal cracking that tends to happen in square openings if things get stressed. All right, pole foundations. Pole foundations. 322. 322. Pole foundations. Let's see where we're at on time. We're at 40 minutes. Let's stop here. Let's stop this one here. We'll start video 3 at pole foundations, because after foundations comes deep foundations, deep piles, and pile foundations, and base foundations, and that ends chapter 3. So we'll have a short video after this one, and we'll stop this one here at pole foundations. Again, I'm not expecting you to be a structural engineer. There'll be a few things out of here that I'll expect you to be able to recite, but don't get all freaked out.